Temperature is a very fundamental concept of thermodynamics. Thermo meaning heat means when you talk about temperature. So what temperature is temperature is it's a measure of the random kinetic energy of the particles in a gas. Or if not even a gas, in anything. And it's important that we distinguish that it's random kinetic energy instead of just kinetic energy, because if I throw a baseball, it's not hotter because it's moving faster. Some of that energy can be converted to heat when it hits something, but while it's moving, it's not heat. So there is our basic definition of temperature. So by random kinetic energy, what I mean is that the particles are all bouncing around all crazy like. There's no specific given direction. In fact, there can't be. Otherwise, like if all the particles are moving in a given direction, that's just called speed, right? That's just like the object is moving, like your baseball is moving. But if your objects they all have a different direction, they're all random, so they're being random, and we're talking about gas, so you have to have lots and lots of particles. That means that they're all as many are going up as they're going down, as many are going left as they're going right, as many are going forward as backwards. If it's going to be truly random and you have a large sampling of particles, that's going to be true. So let's take a look at this simulation I have here from PhET and hope it doesn't break my streaming software. So we have is a very small box on the order of a few nanometers. I'm going to put in some gas particles into here. And right now, the directions are not random. They're all going the same direction. I mean, it's still reading a temperature because it's a simulation, it's set. But when I put these guys in here, and they start to spread out, eventually you can see that they are going all directions. Once they're good and spread out, I mean, there's a bit more over here, so they're going to spread out a bit more to the right over time. But yeah, there's no preferred direction. If you try and track one, it just bounces kind of all over the place. And you can't really predict what it's going to do at any given time. So we're measuring the random kinetic energy of a particle. Temperature is related to energy. And the more energy you have in your system, the hotter it will be. But it's not just energy. It's a function of energy. So, actually, let's go back and look at that software for a second again and say, what happens if I increase the temperature? Add more heat to it, I guess. You can see the temperature is increasing, and you can see that the speed of the particles are increasing as well. On average, you still get some that are going slow sometimes. Where'd it go? Ooh, I lost it. I was going fast. Every so often I see one that's going slow for a bit. So this is an average speed. So just because some of them are going fast doesn't mean other ones are not going slow. So yeah, on average, most of them are going fast. But if you watch, some of them are still going to be slowly moving through here. Okay, so let's talk about how to measure temperature and what units you measured in. So given that you guys live in America, I would expect you are familiar with the Fahrenheit system. So let's put it over here. So it's going to be degrees Fahrenheit. Other systems could be Celsius. You guys are familiar with? Units will be degrees Celsius. And there's two more if you really care. Well, one of them you certainly care about because we're going to use it, the Kelvin scale. And then so Fahrenheit is based off of the common temperatures that a human would experience. So most people would experience temperatures from 0 to 100 throughout the year. Not too many places get below 0 degrees Fahrenheit, and not too many places that spend a lot of time above 100 degrees Fahrenheit. So that's a pretty good range of temperatures for what people, interact with. Celsius is based off of water, so it chooses the freezing point of water to be 0 and the boiling point of water to be 100. The Kelvin scale takes the same steps as the Celsius scale, but is based off absolute 0. So absolute 0 is 0, and then the freezing point of water or the melting point of ice, if you'd rather, is 273.16 Kelvin, and the boiling point is 373.16 Kelvin. We'll do more with that in a second. And the last scale, if you really care about it, which I'm probably never going to mention it again, is the Rankine scale, which, to be honest, I don't even remember what the unit is for it. Probably R or something like that. But I've used it so rarely that I don't even remember. But it is to the Fahrenheit scale what Kelvin is to the Celsius scale, meaning it's the same step as the Fahrenheit scale, but it's based on absolute 0 still. So let's look at the big three: Fahrenheit, Celsius, and Kelvin. And then I want to compare absolute 0. And to be clear, the ones we care more about are Celsius and Kelvin, because this is a science class, and that's going to be a metric unit. That's an SI unit. I care about boiling point. I'm sorry, freezing point. I'll do freezing point first. Mess myself up because I just went in order. Freezing and then boiling. All right. So on the Fahrenheit scale, absolute 0 is negative 459 degrees Fahrenheit, which is absolute 0 is absurdly cold. I guess I'll talk about what absolute 0 is in a minute because I haven't done that yet. On the Celsius scale, we're just going to not worry about the decimals, so it's going to be minus 273 degrees Celsius. And on the Kelvin scale, it's 0. Now, the freezing point for water is what we're talking about because that's what we care about. Is on Fahrenheit, that is 32 degrees Fahrenheit. And then Celsius is 0 degrees Celsius. And Kelvin is 273 Kelvin. And the boiling point of water in Fahrenheit is 212 degrees Fahrenheit. And 100 degrees Celsius, and 373 Kelvin. So I'd like to point out that it looks like the Celsius and scale makes a lot of sense because this is 0 and 100. People like that. But I'd like to point out to you, just because it irks me that people say, oh yeah, this makes so much more sense. It's based off water. What's Fahrenheit based off of? Well, like I said, or Fahrenheit, this will say Fahrenheit's based off nothing. Well, Fahrenheit is based off of 0 to 100 being common temperatures people experience in normal life. So while it's not that useful for science because it's kind of arbitrary, but it's kind of useful for everyday life because, like I said, it's based off of things you might experience. But the Kelvin scale is actually the one we want to use. This is the important one. There are times when you can use Celsius, but only because it's analogous to Kelvin. Kelvin is the SI scale system. So I'm going to write. So default to Kelvin. So if you want to convert from Celsius to Kelvin, just add 273 to your Celsius. Yeah, and I don't think we're going to do any Fahrenheit conversion, so I'm not really going to worry about that. But you can figure it out from this chart if you really want to. So what does absolute zero mean? So if temperature is a measure of the average random kinetic energy of the particles in a substance, absolute zero is the temperature at which they have zero kinetic energy. Ooh. That means there's no vibrations, there's no motion, everything is still, everything is frozen, there is no energy to be found. Now, absolute zero is still theoretical. We've never actually gotten there, but we've gotten very close. I think we've gotten to the nano or even the pico-Kelvin scale, meaning like just so close to zero. But it's also theoretically impossible to reach absolute zero. So we never actually get to something that's truly absolute zero, but we'll get very close, and we already have gotten very close. So it's a concept, but not something that exists in practice. All right, guys, it's been a good little bit in this video, so I'm going to call it quits, and I'll see you in the next one. Have a good day. Make good choices and stay safe out there.